This call is now being recorded.
I haven't recorded it before, so I'm repeating a few things for the online audience who are watching the recorded session. So far we have covered till week 11, and week 12 is application of what we learned so far. So in exam point of view, you won't get much questions from that. So we are going to revise all the concepts from week 1 to week 11 in this three live sessions in this week: Monday, Wednesday, and Friday. So if you have any doubts, or if you feel like you want to repeat any topics, or you didn't understand it clearly, you want to give more practice problems, please feel free to join the live session and ask your questions. We'll solve it right away, and we'll give some more practice problems, reference books, and all for it. Broadly, we covered modeling, time response. So this was a portion for this one. Later, we covered frequency response, controller design, for example, PID controller. This was your portion for week 2, where here the until 4 you don't have. Here the broader topics are root locus, Bode, design using Bode and root locus. Here and PID also comes here, I think. Yeah. For quiz one, you have all the time response analysis, transfer functions broadly, modeling of systems, how to model a system using transfer function, and how to analyze the system. Stability was a very important topic in first quiz content. And what else? Time response analysis, rise time, peak time, along with the steady state error. Uh, for a step input, what is the error for a type 0 system, type 1 system, kind of. Right. Apart from these two topics you studied for quiz 1 and quiz 2, the last topic, very important topic, is state space representation. Because for you to learn the state space representation, the first two blocks are very essential. But instead of using the first two blocks, you will be using this state space representation topic hereafter. If you take a advanced control course, or any course that is related to the control engineering, where control engineering is the prerequisite, then you will be using only the state space representation, all the pole placements, and little advanced controller than PID that you will use. So this considered to be an important topic compared to other two blocks. Right. Here you studied how to go in between transfer function to state space, what are those state transition matrix. And another important topic in state space representation is the pole placement controller that you would have studied in the last week. Pole placement controller plays a very major role, where so far what we have done, if, if this is my time response analysis, and if I want my system to behave like this, so I have to bring this output response from this point of settling time to this point of settling time. Basically, I want to reduce the settling time. So I will see, if previously this was my corresponding poles. Previously, if my poles was here, and for with respect to the green response, my poles might be here, because the based on the concepts we learn, farther the poles, fastest the faster the response, right? So this is the basic concept, very basic things. After learning all these things, we try to connect these points, then come up with this interrelation between each specifications, right? So based on that, if we want to pull the pole from near to the origin to farther from the origin, what I can do, I have to, already there will be some zeros. For example, if this is my pole for a previous controller one, this is the actual plant, let's take. that is in this red color pole. Okay, but I want this response in this green color pole, that is the fastest, so that I can reduce the settling time. So what I can do, I will just multiply this with s plus 10 divided by s plus 10. This is the arbitrary method that we used to do. So arbitrarily, if I want to increase the faster response, I don't have any specific things, but just want to increase the response, like speed of the response, then I will just multiply the same zero with same pole, that acts as a pole zero cancellation with, that doesn't add much, but we will add another zero to pull it down so that it will be compensated. So this can be done either using PID controller or using designing compensators. So far we have been doing all this same work, but in different aspects, different kinds of tools we used. Just in PID controller we would have tuned this KP, KI, KD, ultimately changing the routes or changing the pole location, so that I will get the desired response. In designing compensator, I have included more poles or zeros like this, so that I can change the pole of the system, so that I will get the desired state response. So ultimately the aim is same, but the analysis is different. By using different kinds of methods, we try to do the same objective. Now also we are going to do the same objective, but in different representation, that is in state space representation. In state space representation, we call this as a pole placement method, where in pole placement method, ultimately we are going to do the same thing. If I want to change the poles from black to this green location, then if my closed loop systems poles has to be here in, this is location number 1, this is location number 2, let's take. If my this is open loop poles, if my closed loop pole should be there in location 2, what should be my gain? That's what the pole placement controller helps you to find, right? So in MATLAB, I don't know whether you know this in MATLAB, but in MATLAB there are uh, how you will define this. First, you have to define the state transition matrix A, B, C, and D. D most probably 0, let's take. Then you can define the pole location. So where you want the system pole to be. Then you can find the K, the gain, respective gain, by using this keyword acre of A, comma, B, comma, poles. So this will find the K value or the gain value for the system, proper gain value for the system, so that your closed loop system poles lies in this defined location. Okay, this is what we will do using the Ackermann method. We would have learned 3 different methods of pole placement design, right? So we use different methods to obtain the same results K by hand, or in the MATLAB we can straight away use this Acker formula A, B, and comma poles. Okay. Uh, what else? Own place. And the another important concept that we have covered so far, that was not for this 1 and 2, is this canonical form. So this observable canonical form, controllable canonical form. So these are the 2 different forms. First of all, what is controllability and what is observability? What did you learn so far? Can you answer it in one sentence, or just whatever you understood? What is a basic thing of controllability? If I say my system is controllable, what does it mean? If I say my system is observable, what does it mean? Try to answer that in the chat box. I'll see. Everybody, please type your answers. It's okay if it is wrong or right. Just wanted to see how you understand those things and what is your perspective on that.
So, ma'am, do you want to say, or we should guess about the controllability or observability?
You would have studied this, no, in week
Yes, yeah,
11,
week 11 and 12.
either in lecture notes or in the lecture videos or in
Yeah,
your live
Chakravarti sir
session.
also done that.
He did that last session. So
Hmm.
you just based on your understanding, you can type whatever you understood. You don't need to define it like a textbook, just a layman language, just in our own words. That's fine. Nobody is in the call, or nobody is willing to answer.
Yes, ma'am, doing that.
Hmm, okay. Controllability means the system can be controlled. Okay. Frequent control to reach any state by choosing the right input. Okay, good. You have access to control the system, right? Any other answers, Gayatri? One point to another predictability. Okay. Okay. Any other answers you have? Okay, right. You guess the state that the system from already known inputs and states. Very good. Yeah. Most of you have some good understanding about controllability and observability. Let me just refine the sayings, whatever you said so far. Okay. Controllability is if I want to control a system, I should know whether the system is controllable or not. So, finding whether the system is controllable or not is the controllability test or any test we used to do for checking the controllability. This is a very vague term about the controllability. Actually, what we are trying to do here is we speak in S domain, right? It consists of real axis and imaginary axes, where we explain the nature of any system using its poles, because stability depends on poles. So whether the system is stable or not, that will be decided using the poles. and how well it is going to perform, that will be decided using the location of poles and the location of zeros, right? So if these both systems are stable, right? But which system is going to perform better, that depends on the location of this poles. But both systems are in the stable region. This is where we draw a line in between the stability and the performance. So stability and performance are the two eyes of the control systems. So we will always try to negotiate in between the stability and performance. Sometimes we will go more towards stability if I don't care about performance. Sometimes I will try to take the system to the verge of stability and achieve the most of my performance. It is completely up to my desire, how much I want my system to behave. But there will always be a trade-off in between this stability and performance. You would not get both optimal things. It's very rare, and it will work only at the ideal system that we cannot have in any nature real time systems or any natural systems, right? Coming to the point of controllability and stability, literally what we are trying like, or intuitively what we are trying to do here is, if I have, this is my initial state. So forget about the poles and the zeros for now. This is my initial state. I'm going to speak in terms of state space representation, where we will define the nature of the system or the status of the system using its state trajectory, right? Let's take, this is my initial state x naught, and I want to go somewhere here, that is my state xf. So how can I go here? I can go like this, I can go like this infinite ways, infinite possible ways to go to this from x naught to xf, right? So in any domain r power n, r2, r3, r4 up to r power n dimensional system, if I can steer my system from any initial state to any final state within finite time, that is a very important term here. So controllability tells three keywords: any initial state to any final state within finite time. Then I can say my system is controllable. For example, if I want to go from here to here, x naught to xf within finite time, then the system is controllable. But if I can go from here until here, but I cannot go to the positive axis according to my nature of my system, anything I do. For example, what you will do with this? Whatever value you choose for x, 2, -2, plus -1, you won't be able to go to the positive coordinate of the system, right? For x value. So then the system is controllable or observable? Sorry, controllable or not controllable?
Not controllable.
Not controllable, because I am restricted to positive this value, right? Negative shades of my system. I cannot go. This is in R2. Let's take this is X and this is Y. Let me call this as Y, right? So if my Y is one Y, anywhere you can go. Let's take. So Y can be anything, but X I cannot go from here to here. If this is my XF1, I cannot go to the positive side of my x. So the system is not completely controllable. So it will be not controllable. So this is what the idea behind the controllability is. If I can drive my system to any point from any point, then it is controllable. The reachable is the same, more or less similar, but what you can say is, can a system reach all possible states from a specific starting point? This is controllability is more relaxed version from any initial state to any final state. But reachability most probably start from the origin, and I will check if I can reach all the states from my starting point or specific starting point, right? So it is more narrowed version of the controllability is that reachability. Observability is another concept where it is not related directly related to controllability. If I have a system, I'm giving an input and I'm getting one output. So, with the information or with the knowledge of this input and output alone, if I'm able to find the information about the internal states, then my system is observable. Observable in the sense I can observe my system by seeing whatever it is there visibly outside. This is some layman equivalent term for the observability. For example, if a car is moving from one point to another point, I'm observing the car and I can sense that this car is going at 50 kilometer per hour. If I know the distance it would have covered, then I can say the speed of the car, right? Or I can say at which time the car starts from the origin and sorry, how much time it takes to cover those distance, that I can understand. So this system is observable now only with the outside information or the input and output information. If I can retrieve the internal state information, then the system is observable. Otherwise, the system is not observable. Right. Another person makes a statement that controllable but not observable, right? We will come to the point. I am giving two uh, options for you in between. Okay. How do you map this thing? This is one side, this is another side. How do you map? I want you to map like this or like this. So, how can we make a correct map? Can you say anything about this? If a system is controllable, will it be always observable or sometimes observable or sometimes not observable? Whatever you choose, the other will be the like direct understanding. We choose sometimes observable, sometimes it won't be observable, right? So that kind of. But try to choose the proper pair. If I take this as an if, left side as an if, then will this be which one of this will be the proper answer? If a system is controllable, will it be always observable or sometimes observable? Or will it be always not observable? If controllable, always, sometimes observable.
Ma'am, if controllable, then observable all time.
You're saying if it is controllable, always observable.
Huh. Yes.
You're you're choosing always, right? If
Okay.
one system
Hmm.
is controllable, you're choosing it will be
Huh.
always observable.
Huh. It can be observable. Yeah. Yes.
Okay. Okay. Any other deviation from this choice? Oh, so sometimes okay. Also is choosing sometimes. Right. Any other options? Always, right? Sometimes. Right. So there are two always, two sometimes. Okay. Drag. Okay, thank I'm sorry, I forgot to turn on the mic. Okay, right. Thanks.
Okay, ma'am.
So, what I want to say is the controllability and observability are independent things. Both does not like one does not depend on another. So it can have four different combinations. Like if the system is controllable, the system can be observable or cannot be observable. It doesn't need to be observable. That's what the point I want to make. If it is observable, it need not to be controllable, but it can be. So there are four combination exists. I can have a system that is both controllable and observable, controllable but not observable. This is two category. Observable, not controllable, not observable, not controllable. So these are all the four categories I can have a system. There are many real-time system that comes in this categories. So one cannot depend on the another. You cannot comment about the status of one thing, like whether it is controllable or not, based on the other status. So both are independent. You got the point? Right.
Yes, ma'am.
Okay. But when we design a controller like pole placement controller, as you studied in this week 11 content, it is pole placement controller. So why do we study this controllability is for this. If we want to design a controller, then you will check for controllability. If the system is controllable, then you can design a controller. This is where the catch comes, not in between controllable and observable things, right? And you can design an observer if you can, if your system is observable. That's it. So the steps to do this is, if I ask, I have a system, s plus 2, s my plus 1, let's take, this is my system. This is my actual plan. And I am taking a, I want to design a K. I'm asking you to find a K. This is y of s, let's take, this is r of s. I'm asking you to find a K so that these poles are at s plus 1 into s plus 1, right? 2s plus 1. I want my closed loop poles to be at s plus 3s plus 2. So this is my closed loop poles. These are on my open loop poles. So the first point is, straight away you should not go and find the controller. First you have to check the controllability of the system. Then after checking the controllability, you see if the system is controllable, then you try to design a controller, design a pole placement controller, right? This is why we are doing controllability. This is one part. The similar twin part is, I have a same system and I want you to design a observer, right? So first the point to check the observability of the system. If the system is observable, then you will design a observer. Okay. Right. We will solve few problems on this, and if you have any doubts, I think that will be good. Excuse me. Let me know if he has solved the same system. I don't know what problem he has taken. We are referring to the same book, so there might be a chance. Okay. First of all, the question is the system controllable? They have asked this question. Otherwise, also you have to do this checking whether the system is controllable. First, we need to find whether the system is controllable or not, right? How do you find whether the system is controllable or not? What is a test? Do you remember the name of the test we do? Ackerman's test, kind of three different tests we have, right? What do we do? Anybody? C is equal to.
We know only one, ma'am.
Okay, you learned only one. Okay, you tell that.
That B, A, B, A power.
B. Yeah, based on the nature of the, or sorry, based on the order of the system, we will choose that, right?
Yes, ma'am.
Okay, this is what, with how many order is that the system is? What is the order of the system?
2.
Two. So we will take only B and AB. If it is 3, then A square B will come, right? This is A matrix, this is B matrix, and this is C matrix that we know, right? So the controllability, this is capital C, controllability matrices. You have to write the B matrix as it is. So my screen is visible, right?
Yes, ma'am.
So we have to write this B matrix as it is here. So I'm going to write 1, 2 as the first column. And the second column represents AB. So I'm going to multiply this A into B, and then I'm going to write that multiplication AB here. So A into B, what it will give? 0, 1, 5 minus 1 into B is 1, 2. So this will give me 0 into 1, 0, 2. This is 2 cross 2 matrix. This is 2 cross 1 matrix. So I should get 2 cross 1 matrix, outer product. This is the outer product, and that is the answer you will get out of this matrix when you multiply. That you would know, I hope. 5 into 1, 5. 1 into minus 1 into 2, minus 2, 3. So if I make any mistake, let me. Okay, this is my controllability matrix. So if I find the rank of this controllability matrix, and if the rank is equal to the order of my system, then the system is controllable. Otherwise, the system is not controllable. Right. How to find the rank of the C matrix? It's a determinant of C, right? For determinant also works. That is a shortened method. Otherwise, you have to find the row echelon form and find. Since it is a two cross two matrix, I am going to find the determinant of C matrix, and if it is not equal to 0, then also the rank is full. It's a linear algebra concept, so I'm going to do that. So determinant of C is equal to 3 minus 4, which is minus 1, which is not equal to 0. So the system is controllable. Okay. We found the system is controllable. Now we are free to design a controller. That is going to be your next question. You are asked to find a controller for the system. The controller we are going to design is the pole placement controller, where we will change the gain of my system according to the location of poles I want in my closed loop system. So pole placement controller is the next question. How they have designed this question is, if the system is controllable, please stop me then and there if you don't understand things. Okay. They have given the gain, but I want you to find the gain. I will try to redefine this question. If I put it as S square plus u design a controller u equal to kx, where k is k1 and k2, because this is a second order system. Your states are x1 and x2, and you are supposed to design a controller with input u equal to minus kx, such that I will get the closed loop pole location at s square plus 2, 4, 5, 6, 6s plus it is 6 plus 10, 16 minus 5, 11. So this is going to be my closed loop pole location. So you are supposed to find this K1 and K2, so that if I find the closed loop poles location, for example, if this is my system is x dot equal to ax, right? This is my system. I am giving one input u and I am getting one output y, and I have a feedback that is k. Okay, this is negative, this is positive. So I want you to design this yu as u equal to minus kx, where x is this state of the system. So you want to take back your state information and give it again as an input back to the system. So how it will look like: x dot equal to a x plus bu, where a x plus b into your u is again minus kx. Then overall your system will look like a minus bk into x, right? This x dot now has changed from ax to x dot equal to a minus bk into x. So this is the additional term in your system now. So you have to choose this k, so that your closed loop, this poles, previously this pole is somewhere in x location. Now you want to design that k such that your closed loop poles will be at this location. So how can we do this? Any idea how we do this?
You write the characteristic equation and then
We'll write the characteristic equation. Then I have written
make 11 plus k1 and 6 plus k2
11 plus k1, 6
equal
plus
to
k equal to
oh no ma'am, this is not, this is the final characteristic equation.
yeah.
So I was talking about the first open loop.
Okay, right.
It's Si minus A.
That's what I was trying to get. So here, instead of Si minus A, here what do we have? Si minus A minus Bk, right?
Yes ma'am.
So this will be Si minus A plus Bk. So you have to write this as an equation. So this will be x dot equal to A minus Bk into x. Instead of that, you have to write this. So usually, if we are given with k1, k2 value, how we will write this? A is our what is the A matrix? 0, 1, 5, minus 1. 0, 1, 5, minus 1. This is A, minus B is 1, 1, 2 into k is k1, k2. This is how we write, right? B into k. So this will give me 0, 1, 5, minus 1, minus of this is 2 cross 1, this is 1 cross 2. So 2 cross 2 you will get k1, k2, 2k1, 2k2. This will be 0 minus k1, 1 minus k2, 5 minus 2k1, minus 1 minus 2k2. This is your a minus bk value. So when you take a determinant of this, what you will get? Minus k1 into, sorry,
Yes, ma'am. Yes is coming. Yes is there.
s will come, but I'm trying to get it back. Si minus a we have to write. Before that, I'm calculating whether I'm getting it correct or not. Minus k2 it would be minus of. So this will be k1. If I put k1 equal to minus plus 2 minus 4, it is correct. Minus 2 minus yeah, right, okay. So what you will usually do, we will do is minus pk. So this will be yes minus of k1, sorry, yes plus, it is already minus there, right? So it will be s plus k1, 1 s minus 1 plus k2, s minus 5 plus 2 k1, s plus 1 plus 2 k2. Any mistake I did? No, right? Hope it's correct. Right.
Yes, ma'am.
Right. Now you will find the determinant. S plus k1 into s plus 1 plus 2 k2 minus s minus 1 plus k2 into s minus 1 plus 2 k1 equal to 0. This gives me s square plus s plus 2s k2 plus s k1 plus k1 plus 2 k1 k2 minus s square minus 5s plus 2s k1 minus s plus 5 minus 2k1 plus s k2 minus 5k2 plus 2k1 k2 equal to 0. S square is done. Okay. That's also I have done. Right. Now a square terms, this a square, this a square will get cancelled. Are there any other a square? It is not supposed to be cancelled.
Oh, that yes won't come, ma'am.
Where?
Column number 2, first row,
Okay, here.
the matrix.
Okay, here, right?
Ah, yes, ma'am.
What it will come?
Oh, only minus 1 plus k2.
Oh, okay. Sorry. Okay, right. Here also it won't come, right? It's a
Minus 1 will come. Minus 1.
it's right like this. So it
Ma'am,
will be
minus 1 will.
yeah. Right, thanks. Okay. This is a dumb mistake. Okay. Now it is s plus k1 into s plus 1 plus 2k2 minus of minus 1 plus k2 into minus 5 plus 2k1 equal to 0. Now it is s square plus s plus 2s k2 plus k1s plus k1 plus 2k1 k2 plus 1 minus, sorry, plus minus of 5 minus 2k1 minus 5k2 plus 2k1 k2 equal to 0 a squared plus s plus 2s k2 plus k1 s plus k1 plus 2k1 k2 minus 5 plus 2k1 plus 5k2 minus 2k1 k2 equal to 0. Right, now separating all the terms. What are all s terms? Yes. Where else s is there? This 5k2 only, no? There is no s term here. Nothing. It won't come. It's just a constant, right? Okay. Now is 1 plus 2k2 plus k1 into s. Rest of the terms are constants. Plus 2k1 plus 5k2. This 2k1 and this minus 2k1 k2 will be cancelled. So this won't come. K1 plus 5 plus 2k1. This 3k1 it can be 3k1. I'm writing this to k1 and as 3k1. 3k1 minus 5 minus 5. What else? Plus 5k2 equal to 0. So these are constant terms. Now compare this against your like closed loop characteristic equation. So this will give me 1 plus 2k2 plus k1 equal to 6. This against this against this. So 3k1 minus 5 plus 5k2 equal to 11. Just rearranging all the terms. 2k2 equal to 5. 3k1 plus 5k2 equal to 16. So how can I write this? I can write minus 3k1 minus 6k2 equal to minus 15. 3k1 plus 5k2 equal to 16 as it is. This will go k2 equal to 1. Substituting this back in the first equation, k2 is 1, then 2k2 equal to 4, k2 equal to 2,
Minus K2 equal to minus 1.
k2 equal to minus 2,
Minus 1.
minus 1. How? If I substitute it here, k2 is equal to 1, k1 equal to 3, right? Yeah, again I found k2. Now I found k2. So k1 plus 2k2 equal to 5. The first equation is right. K1 plus 2 equal to 5, k1 equal to 3, right? Correct? If you have any other answers you are getting, let. So now we design, there is a system that x dot equal to ax was my original system, and I designed a k such that my closed loop system, that is x dot equal to a minus bk, has a location, pole location, corresponding characteristic equation like this. For that, the k value I have chosen is 3 comma 1 or 3 1, no dot. So this is how we define the controller. Controller design in the sense we will find the gain of the controller. That's what the controller design is. Now I am going to ask the next question, that is the system observable? We found it is controllable. Now we are going to see if the system is observable also. We know both are independent, right? So observability matrices can be written as C, CA up to CA power n minus 1 of your order. Now it is a second order, so I'm going to find only C and C, where C matrix is here. Which one is C matrix? 1, comma 2. This is my C matrix, right? So A matrix again I have to complete. I will memorize that also. 0, 1, 5 minus 1. 1, 0, 1, 5 minus 1. C 1, 2, 0, 1, 5 minus 1. Right. Now if I write C matrix, it will be 1, 2 as it is. The row I will write as it is. C into 2 is, C into A is 1, 2 into 0, 1, 5 minus 1. This is 1 cross 2, 2 cross 2. So you will get 1 cross 2 or outside product or out product. 0 plus 10, 1 minus 2 minus 1. So it will be 10 and minus 1. Now your observability matrix is 1 to 10 minus 1. Now you want to find the rank of the observability matrix and check if it is equal to your order of the system. If yes, then the system is observable. Otherwise, the system is not observable. Instead of finding the rank, I am going to find whether the observability matrix determinant is not equal to 0. It's easy to find for the 2 cross 2 matrix. It will be minus 1 minus 20 is minus 21 not equal to 0. So the system is observable. So this kind of system is both observable and controllable. Okay. Any doubt in this question? So if I give you a state space representation and ask you to find whether the system is controllable, observable, and to design a controller for the system, will you be able to do?
Yes, ma'am.
Right. Everybody is confident in this, or do you have any doubt in this? Because the portions after your quiz 2 carries a larger weightage in the in semester exam. So you have to be more cautious in this portion after quiz 2. So please be prepared all the topics one by one, like how to convert from system state space to transfer function back to state space, how to write a state space representation of a system. For example, if I give you a mass spring damper system, will you be able to write your state space representation straight from the system? That you have to, because time is also a concern, right? Every time you cannot write a transfer function and convert it back to the state space. So practice how to transfer or how to convert from nth order differential equation to n single order differential equation. I remember that I took this with the week 10 content. So please revise those concepts, practice it instead of just seeing those questions. And when you are seeing that answers will be everything will be easy. Oh, okay, this I can do. But when you really try to solve the problem, then you will get lot and lot of doubts. So please practice before coming to the exam. It gives enough time to prepare. Now, if in the second question, I have given the closed loop transfer function, right? Now, I am giving this is another type of the question where I will give the K1, K2, and I will ask you to find the closed loop transfer function. Will you be able to do? I'm giving K1 and K2 for the same system, same concept, U equal to Kx. So your U should be U equal to 2 of X, X1, X2. Then this will be 2X1. This is 1 cross 2, right? This is 2 cross 1. Then it will be 2 cross 2. This is your U. So when you write in terms of A equal to minus BK of X, you should be able to write A minus B into K will be 2 into X. So A, B matrix the original matrix that we saw, no? This is A, 0, 1, 5, minus 1. A is 0, 1, 5, minus 1. B is 1, 2. So previously what we used to do is S minus A plus BX. Then we found this characteristic equation. From this characteristic equation, we found the K1, K2. The same thing we are going to do, but we don't need to, we will straight away put the K value and find the characteristic equation instead of knowing the characteristic equation and equating it, right? The steps will be the same. So you will have 0, 1, 5, minus 1, minus of 1, 2 into K was given 2, 2 whole into x dot equal. So what you will get 0, 1, 5, minus 1 as it is. This is 2 cross 1, 1 cross 2. So 2 cross 2 you should get 2, 1 into 2, 2, 1 into 2, 2, 2 to 4, 2 to 4. So this is your B into K. This is your A. Now 0, minus 2, 1 plus minus 2, 5 minus 4, minus 1 minus 4. This is your minus 2, minus 1, 1 minus 5. So this is your A minus BK. Now you have to find SI minus A minus BK. So this will be SI minus A plus BK. So please don't confuse with the terms. What it will give? S minus 2, 1, minus 1, S plus 5, right? So S plus 2 into S plus 5, minus of minus 1 plus 1, S square plus 7S plus 10 plus 1, S square plus 7S plus 11. Right. This is your characteristic equation. Okay. So two ways we have studied. If they give the gain and ask for the characteristic equation, or they would ask something like, what is the position of phi? What is the position of S, coefficient of S, or what is the coefficient of S square, or what is the coefficient of constant term? Then you should be able to derive all this and find the characteristic equation and to answer in MCQs because it is a computer based exam, right? In MCQ or short answer, you will be answering this particular method. So if you do any mistakes here, ultimately you are going to answer this. This is the disadvantage of the computer based exam. If you have done all these steps correctly, still if you make some mistake here, for example, I might be doing S minus 2, then I will get different answer here. You will lose 3 marks as it is. This is what happened in previous quiz and all. So please be careful while calculating each and every steps. Know what formulas we have to use, what procedures we have to use before and go for the exam. I will
So,
give
why,
you.
ma'am, we could have had it as a pen and paper, no, ma'am.
No, it was not very feasible for us because we fixed step markings like we have one style of correcting things, right? Then people have asked that I have written formula, I made mistake in the answers, but give marks. That's not fair for everyone, right? So we
Okay.
convert everything to a computer based exam
Okay.
because we have different methods and there exists different steps for each methods. So finalizing a step mark for particular one method is very difficult in control engineering course. So we switch back to computer based. Whatever method you can use, your answer should be correct and you will earn marks for those steps. You should be careful while solving the problem. That's the ultimate goal.
Okay.
Okay, then I'll give you 2 minutes. We'll also take a break and we'll continue. by 345. Okay, we are back. Let's solve some more problems. For a given state space system, for example, x dot equal to 0, 1, minus 6, minus 5. So if you see control engineering by Ugata, you would see many examples in the state space system. Excuse me for a minute. Okay. Right. This is my state space representation. X. What I was saying that if you see this control engineering by Ogata book, you would see many solved examples on every problems. Even for root locus, Bode, designed by root locus, designed by Bode, all state space system, controllability, observability, and this pole placement controller, canonical forms, everything you would find. And There is another important topics like simultaneous controller, observer based controller design. That everything you see in that book. That will be helpful. So this is my system, right? Okay. And my output matrix is 1, 0 and x. The question they're asking is design a controller such that u equal to minus kx. It's a state feedback controller. K equal to, we call this as pole placement also. Actual technical name for this is a state feedback controller because we are taking a state x dot equal to ax. We are taking our state back as a feedback and give back as an input, right? So that's why it is being called as state feedback controller. Okay, design a state feedback controller such that k equal to k1 into k2 such that its closed loop poles. Usually how they will give the closed loop poles either as a pole or as a characteristic equation. From there you can find the poles. Here they are giving it as a damping coefficient. Closed loop poles in the form of damping coefficient zeta equal to 0.707 and step response peak time. The step response is important because if you don't know the what response it is, we cannot find that steady state error and value, right? So it is 3.14. Peak time is 3.14. They are asking what is the natural frequency omega n of the system with this desired closed loop pole. Maybe rounded to two decimal places. We don't care about it, right? Now, consider you have to find this closed loop pole from this given information. That is the first step. And from that characteristic equation, you have to find back the k as we did in the previous problem. Only thing is, in the previous problem, they have given the characteristic equation as it is. Now we have to do one extra step to find the characteristic equation, and then from there we have to find the gain of the controller such that it is u equal to minus kx for the state feedback control. I hope the problem is clear to you, right? If not, let me know.
Yes, ma'am.
First, we need to find the characteristic equation. What is the characteristic equation's general representation? It is s square 2 zeta omega n s plus omega n s square equal to 0. This is the second order transfer function because it will look like this. This bottom we call it as characteristic equation, so it is that. So here zeta information is well known. Only the unknown information is this omega n that we need to find from the given information tp that we have to relate with this. What is the relation between tp and omega n? Formula you know, pi divided by omega n into 1 minus zeta square. Otherwise we call this simply pi by omega d, where omega d is omega n into root of 1 minus zeta square. So here you know pi. You don't know omega n, but you know TP 3.14. Root of 1 minus zeta square. Zeta square also we know, right? It is 0.707 the whole square. Square is inside it. Okay. Now keep omega n here. 3.14 here. 1 minus 0.707 into 0.707. Calculator 0.707 into 0.707 is 0.49 and it 1 minus of answer. It is 0.500 some 500.5 instance. So into 3.14. This is 3.14, this is 3.14, it is 1 by 0.5. It is easy for us to calculate, right? And this will give me 2. right? Oh, square root is there, no? So it will be 2 root 2. So your omega n is root 2. So your characteristic equation is s square minus, it is plus only, no? Root 2 into 0.707 s plus root 2 square, it is 2. Root 2 into 0.7, how much is around 0.1 s square plus 1s plus 2. So it is s square plus s plus 2. Right? That's your characteristic equation. So from this, you will be able to find the K1, K2, right? Can you solve with me? Just for a practice. We did in the previous problem, right? We are going to do the same thing. For you to understand this concept, we took this problem. So this is A matrix 0, 1, minus 6, minus 5. P is 0, 1. Okay. Can we find the K1, K2 now? Or is there any other step in between? Can we straight away find, or is there any other step? Anyone? I think everybody's sleeping. We need to find.
Si minus a became.
Yeah, first we need to find the controllability, right? If it is controllable only, we can find the controller. There is no point in finding controller if it is not controllable.
Oh,
So we need to do 0, 1. B is 0, 1, 0, 1 minus 6 minus 5, 0. Just 2 plus 1 plus 2. 2 plus 2, it will, 2 plus 1, it should give. B, oh, B, A, B line. Every time I got confused. 0, 1. Then it becomes 0, 1 minus 5. 1 minus 5. It is controllability matrix. It will be minus 0, minus 1, not equal to 0. So the system is controllable. Then we are going to find the k value, that is a minus bk into x dot equal to, where it is a is 0, 1 minus 6 minus 5 minus b 0, 1 into k, I don't know, k1, k2, 0, 1 minus 6 minus 5 minus of 0, 0 minus k1 minus k2 plus 1 day, but outer minus it is there. So 0, 1 minus 6 minus k1 minus 5 minus k2. This is your A minus BK matrix. Now what we are going to do, Si minus A plus BK matrix we have to find. it will be S minus 1 plus 6 plus K1, S plus 5 plus K2. Now S into S square plus 5S plus K2S minus 6 minus K1 equal to 0. S square plus 5 plus K2 into S minus 6 minus K1 equal to 0. So now the characteristic equation what we found?
Plus
Yes,
6 came.
plus 6 it is. No, this is minus, so minus of minus, no? Right, it is plus 6 plus K1. Right, thanks. It will be compared against this characteristic equation we found before. So it is 5 plus K2 equal to 1, first equation. 6 plus K1 equal to 2 is the second equation. K1 is the, oh, no K1, no K2. Okay, straightforward. K1 is equal to minus 4. Sorry, K2 equal to minus 4. K1 equal to, it is also minus 4. Just see if I have missed something. Yeah, it is because this,
The gain is negative means does it carry any specific meaning? Like,
which one, which one?
we are getting negative values now. Minus 4, minus 4.
Ah, that doesn't mean anything. Nothing. Like not in terms of controllability. So
Okay.
it's just tuning value. Okay, no, that's not a problem. Okay. We found this K1, K2 as minus 4, minus 4. Good. This is the gain of the system. The equations. Okay. This is one different question than we used to solve. Can we check whether the system is observable? Observability my C is 1, 0. So if I check it is 1, 0, your A matrix is 0, 1, minus 6, minus 5, right? CA, so 1, 0, 0, 6, minus 1, minus 5. I think this is the matrix. 0, 1, 0, 1, minus 6, minus 1. Okay. If I take this will give me 1 into cross 1 matrix. It will be 1, 0, 0, 1, 1, 0, 1. Okay, rank will be full rank test. Rank equal to 2. Okay, it is observable. I thought it won't because the one term in the B matrix is 0. Okay. Now we will solve some other problem. Okay, we'll solve one problem in linearization that is a real world problem. Consider a pendulum cart. Pendulum cart is pendulum, you know, right? Pendulum is we have a clock that has one what do you call it? Some stick or something like that. So there is some rod, and at the end of the rod there will be a ball kind of structure where it used to go from one place to another for every second. So previously in olden days we have this pendulum clock where for every second it will go from one point to another point making a click sound, and when it comes here, from here it is 1 second, another if it goes here it is 1 second. It is calibrated to do that. So if it goes 60 times here and there, then it comes to be 1 minute. So that's how the pendulum clock is. Now we have a cart. Cart pendulum is, this pendulum will be, instead of attached to a wall or a clock, it will be attached to a cart. So that the cart will be moved. I will give a force to this cart. I will make the cart to move from here to here so that I will get the same oscillation of the pendulum. So instead of a constant point, this pinpoint is constant, but I'm controlling the pendulum. Instead of using a battery, I'm going to use a force by my hand. I'm going to push the cart so that the cart will go front and back. And based on that, my pendulum is going to oscillate here and there. So this is the nature of the system. I'm giving it to you. There are another system that has inverted pendulum. So it has a cart. It is connected to the same pivot, but the pendulum is supposed to be stabilized at the straight point instead of other points by moving the cart from one point to another. This is like in our childhood days, we used to balance our umbrella inside the palm of our hand, right? We will move our hand front and back so that we will try not to put the umbrella down. Like the umbrella should not fall down, so that we will try to stabilize the umbrella by moving our hand. This is the concept of this inverted pendulum. This is very much interesting problem in terms of missile launch and all. The missile launch has the application of this inverted pendulum similar to that. If you want to launch the missile at a particular direction, then they will calculate or they will approximate the system similar to this. Okay, coming to our example. So this is a similar real-time system. I'm taking a real-time system with a cart. Cart is just a wheel kind of vehicle, toy vehicle. Okay, I have a pivot here and my pendulum has been connected to the pivot and it has a ball at the end. So my pendulum will go oscillate from this point to another point as my cart moves from left to right. So this length of this pendulum, here it is, no? This I am going to call it as L. This is the length of the rod. And the pivot and the oscillation it is going to make, this is the rod. So it will come from here to here and again go from here to here. So this angle I am going to call as theta. If the pendulum is here straight, then the theta is 0. Otherwise, whatever movement it is taking, the theta might change. That's how I'm framing. And I'm calling the mass of my pendulum as m. Now we are trying to this is an objective based question, but I'm going to do step by step so that you'll get answers in each step. So consider this pendulum cart. It consists of a hinge that can move in the direction z. The direction is this. This is the direction of. We call it as z. So it is going to move in this direction. Okay. Right. And there it is. And the Tereto attached pendulum. And the system is described by the equation. So equation also has been given in the question. Okay. That's easy. Actually, we are supposed to form this equation based on the free body diagram of the system, but in the question it has been given, so we will just simplify it. So this is the g sine theta minus z double dot, it's double dot, right? Cos theta equal to 0. We know all these physical forms, right? Theta is the angle of the pendulum is going here and the angle it is making here. And g is the gravity constant, z is the direction. Instead of x, we are going to use little different variable here. Just c, that's it. Z, x, everything is same here. And theta is the theta we already defined. So if theta is position, let me ask this. If x is position, how do we call the x dot?
Velocity.
Speed.
Velocity. V.
Velocity.
How do you call the x double dot?
Acceleration.
Acceleration. Similarly, if theta is an angular position, how do you call theta dot?
Angular velocity.
Same. Angular theta double dot is angular acceleration.
Acceleration.
So this is angular acceleration and this is your linear acceleration. right? Instead of x, it is z. So linear acceleration, the cart will be accelerate at a rate of z double dot. The pendulum will be oscillate at the rate of theta double dot. This is the physical interpretation behind this equation. And it depends on that angular velocity depends on L, and your linear acceleration depends on your theta in terms of cos. Okay. Now, what is the question? This is the equation given defining the state variables. Okay, which of the following statements are correct? Okay, the option I will read out and we will find it, right? They have given an equilibrium point, x equilibrium point and u equilibrium point, that is for control. They have given two options and asked us to find whether which of that is the correct equilibrium point. And the next two options are what is the correct local linearization representation of the system with respect to the equilibrium point. So the question now wants us to find the equilibrium point as a first one. Second, we have to locally linearize the system around its equilibrium point. So right now we have a differential equation. If I want a state space representation of the equation, what I will do? You know all the steps. Just I'm going to help you write the sum you are going to solve. This is a differential equation that is of nth order, second order. Right? It is theta double dot z double dot. Now what you want to do? You want to convert it into a nth order to nth order to what do you call?
First order.
N single order differential equation. So it is second order. So two single order differential equation we need to form from that. So this is very important. Please practice this. I'm telling this again and again whenever I'm solving this. When you learn nonlinear systems and all, this will be very much helpful to you. So first, I'm going to define the state equation. Now I'm going to take x1 as theta and x2 as x1 dot, that is equal to theta dot. Now I want to call, and actually this is given in the question, so I will just write as it is. They are taking z double dot by L as a u, that is the input, acceleration input you are giving, that is the interpretation. Y equal to theta. Y is the another variable. For converting nth order to n differential, n single order, we use this. And they are defining another term, that is to simplify, that is root of g by L. This will be useful when we define the equation, right? So these are given in the question. All this information have been given in the question. Now what we can do? Now we have to find the equilibrium point. For that we need to convert it into a state space equation first of all. Then we can convert it into a, and to find the equilibrium points around it. So the state space equation is L theta double dot G sine theta plus Z double dot cos theta equal to 0. So I'm taking theta double dot as it is and putting all the, multiplying everything by L, because I don't want any coefficients for my theta double dot. I'm going to equate it there. So I'm multiplying everything by L, and that will also make my life easy because zeta double dot by L it was given. So I want this to somehow zeta double dot by L so that I can use a shorthand notation. Theta double dot plus G by L, what it is? Root of G by L, root of G by L is omega naught. So G by L can be written as omega naught square into sine theta. Just it was given in the question. If it is not given, then we can straight away use the nth order differential equation as by keeping g by l as it is. No need to convert it into omega square. Just because it was given in the question, we are doing it. Right. Z double dot by L can be replaced using this U cos theta. Now it is more simplified than before. Now how do you define this? If I take x1 is equal to theta, as it was given in the question, x1 equal to theta, x1 dot x2 equal to x1 dot equal to theta dot. So x2 dot equal to theta double dot. So this theta double dot can be written as x2 dot. So I'm keeping everything except theta double dot in the right hand side. So minus omega naught square sine theta minus u cos theta. Right. So the x1 dot is always x2 when we are converting to single order differential equation. Omega naught square sine theta will be replaced with x1. Sine x1 because there is no theta. I want to convert everything into a same variable. U cos x1. So this is ultimately the state space representation of my system. What is system? Cart pendulum system. Right. I want to split this in terms of x dot equal to ax plus bu dot. How can I split x dot, x1 dot, x2 dot equal to x2 minus omega naught square sine x1 plus minus u cos x1 0, right? Because there is no u term here. So this can again be written as 0, 1 minus omega square. Okay, this cannot be written because it is in a non-linear equation. So maximum we can write it like this. Now what is the next step? We will linearize it. When we are linearizing around its equilibrium point to find the state equilibrium point, we will consider u equal to 0 always, right? So this whole equation becomes x2 minus omega square sine x1 plus 0. So only this simplified term. How do we find the Jacobian equation? J is equal to dou x1 by array. Dou x1 dot by dou x1, dou x1 dot by dou x2, dou x2 dot by dou x1, dou x2 dot by dou x2. There is a chance that I may make mistakes here. So let me know if it is. So dou x1 dot by dou x1, there is no term. X2 is 1. X1 is minus omega square, which is not dependent on x1. Sine differentiation of sine is cos x1. There is no x2 term, so it is 0. Right? This is my linearized system. The important point is we forgot to find the equilibrium point. So then only we can linearize this system, right? How do you find the equilibrium point? You will equate this equation x1 dot equal to 0, x2 dot equal to 0. So x1 dot is x2, which is straight away equal to 0. X2 dot is omega minus omega square sine x1 equal to 0. So for what values of x1, this x2 dot will be equal to 0. That's what we are going to find. For what value of x1, x2 dot is equal to 0. What can be the value of x1 that makes x2 dot equal to 0? Sine 0, 0.
N by.
Sine n pi will be 0. So the equilibrium points are 0, 0 is a one set of equilibrium point. Equilibrium point 2 is 0, n pi, right? N pi, 0. 0 not included. So these are the two set of equilibrium points. Equilibrium point 1, point 2. So you need to find the linearized version of the system for both equilibrium points. So the Jacobian is, I will just rewrite this 0, 1 minus omega square cos x1 0. So the first linearized version is J1 at 0, comma 0. 0, 1 minus omega square cos of, instead of x1, I am going to put 0 at 0, comma 0. Cos 0, 1, right? 0, 1 minus omega naught square, 0. So this is your first localized linearized system, local linearized system. Second is should be evaluated at n pi comma 0. So 0, 1 minus omega square cos of n pi 0 at n pi comma 0. Right. This will give me two values. One is minus omega m square into plus or minus 1, because when the pi is equal to odd, 1, 3 and all, n pi, when pi is odd, cos of pi will be equal to minus 1. When the pi is even, cos of 2 into pi is equal to 1. So this keeps oscillating. So your system might go from plus or minus omega naught square. That is your J2. So this is your second localized linearization. Now, there might be question to ask whether your linear system is stable or not. For to answer that, you need to find the eigenvalue of J1 and eigenvalue of J2. So if the eigenvalue of J1 is less than 0, stable, greater than 0, unstable. Same for this. Stable, greater than 0, unstable. But there is nothing about it in another question. Okay. This is how
Yes, ma'am.
linearization based question comes. So in this topic that has been covered after quiz 2, you have this pole placement based design or controllability observability checking, equilibrium point, finding an equilibrium point, localization around your equilibrium point can be another possible question. So practice this kind of questions today, and we'll solve whole problems in canonical form and all. And also we will revisit some root locus based and mode based question in the Wednesday session. Okay. And please, you also solve few problems on that and come up with questions. We can discuss that also. We can conclude the meeting if nobody has any questions. Anybody has any particular questions? Okay, then you can leave.
Thank you, ma'am.
Thank
Thank
you.
you, ma'am. Good night, ma'am.
Thank you, ma'am.
Thank you.